G'day viewers. In this episode I'm going to talk to you about the Hubble tension and how I believe we've solved it, in fact conclusively, and I choose my words very, very carefully. Okay, first of all I'll explain what the Hubble tension is. So the Hubble tension is basically the discrepancy between two measurements of the same thing. So there's one method which is based on the cosmic distance ladder method. So basically, to cut a long story short, it's about using very bright objects to measure the expansion rate of the universe. The second method is uses the cosmic microwave background radiation to actually determine the expansion rate of the universe. Now, in 2008, the official particle data group value of Hubble constant was 73 kilometers per second per megaparsec. Now, in 2008, I published an article with the Australian Institute of Physics where I predicted that the true value of the Hubble constant, the cosmological Hubble constant, was 67.1 kilometers per second per megaparsec. So I'm saying it's 67.1. At the time, mainstream was saying it's no, it's 73 kilometers per second per megaparsec. Now, at the time when I came up with that number that was published, I was thinking to myself, oh well, it's a little bit off, should I go ahead with getting this published? And at the time I was in two minds about it, but looking back now, I'm very pleased that I actually did it. So I just want to cover that off again. In 2008, the official value was 73 kilometers per second per megaparsec, and in 2008 I published a prediction of 67.1 kilometer per second per megaparsec. Now, in 2013, the Planck satellite was launched, and the Planck satellite measured a value of 67.3 kilometers per second per megaparsec. So the official value in 2008 was 73, and then the official value in 2013 suddenly became 67.3. So it matched my prediction almost precisely, and I was very pleased about that. And what that did was validate in the latest paper that I've just completed. It validated equation 1. So equation 1 was derived from first principles utilising Buckingham Pi theory, and I've got to stress there's nothing more first principles than Buckingham Pi theory. It is more first principles than the Einstein-Hilbert action. So physicists tend to think that it's just dimensional analysis. No. It is far deeper than that. And if you take a look into the theory, you can see for yourself. And just a point on that, something that might help you to learn: Buckingham Pi theory starts as a theory, but then after the first step, it turns into a theorem. So the theory part of it is the variables that you choose, and that's a very personal, individual choice. There's no right or wrong about it. You can choose the size of grapefruit and try and relate that to the size of the moon or whatever. It's entirely up to you. So it's up to the individual to choose those variables. That's the theory part of it. But then once you've decided on what your key parameters are, you then use that's when the theorem kicks in, and that's when you start to actually mechanically execute the steps of the theorem to get your overall equation. So I just wanted to sort of mention that a bit, because my reading, my take on physicists' understanding of Buckingham Pi theory is that they do not understand it in any way, shape or form, not properly. but it's it has been the bread and butter of a number of branches of engineering for the last 100 years, ever since Edgar Buckingham actually came up with it. Okay, so we used Buckingham pi theory to derive equation 1. Now, equation 1 looks very complex, and indeed it is complex. It took quite a long time to derive, because equation 1 is actually the final step in a long chain of derivations that I needed to do first. So you've got to remember that equation 1, which works for cosmology, actually started as a particle physics problem. So from particle physics, I was able to derive equation 1, and the way I did that was by taking my particle physics equation, which I derived from first principles and predicted the size of the proton, neutron, etc., and scaling that up. So I literally took that same equation and then I scaled it up to cosmological size, and hence I ended up with equation 1, which you can see in that paper. Okay, so what I then did after I came up with equation 1, and by the way, equation 1 was first published, was first derived in 2006. I then published it in 2007 in one of my books, Quinta Essentia, Part 4, A Practical Guide to Space-Time Engineering, Part 4. And that was 2007. So it was first derived in 2006 and published in 2006 in an early edition of that same book in 2006, then republished again in a later version, an updated version in 2007 of the same book. Then it was published again in 2008 by the Australian, the result was published by the Australian Institute of Physics in 2008. And that's all part of the historical record, and you can look that up if you're interested, or if you're not, you can just reach out to me. So that equation generates the what I call the cosmological Hubble constant. So it's the CMBR version of the Hubble constant. That's how I derived it, and it was derived initially specifically for use with the Milky Way galaxy. So I used the Milky Way galaxy as my reference particle. I then scaled that up to the size of the cosmos, and that scaling resulted in the cosmological Hubble constant, the CMBR Hubble constant. Okay. Now after that, some time later, I decided, well, look, I'm just curious. I'm just going to plug some galactic values in and see what I get, And I did that, and I wrote a paper. Actually, I wrote a number of papers. One is called the CMBR Constrained Milky Way Galaxy. So you can use this same equation to constrain the mass of the Milky Way galaxy to the cosmic microwave background radiation temperature. And when you do, you get a result of around 6.4 by 10 to the 11 solar masses. So it sits in about the bottom third of the spectrum of estimates for the mass of the Milky Way. Anyway, you can use it that way. So I wrote a paper about that. I also wrote a paper titled The Cosmological Significance of Massive Photons, where I used that same equation to demonstrate how significant massive photons, because that equation carries a massive photon term in it. So that experimental validation by the Planck satellite in 2013, actually, because it validated the equation, as a consequence of that, it also validated the predicted mass, my predicted mass of a photon. So not only did it validate the Hubble constant, It also validated my prediction for the value of the CMBR, because in that same 2008 publication by the Australian Institute of Physics, I predicted the Hubble constant. I predicted an order of magnitude improvement in the resolution of the cosmic microwave background radiation temperature. So both of those are what's called a priori predictions, experimentally verified. So you make a prediction in advance, and to be honest with your viewers, that's actually the gold standard of science. Right? It's what everybody tries to achieve, but very few people do in their lifetime. So it's sorry to blow my own trumpet, but it's actually quite an achievement. Now, in doing that, in having those two a priori predictions, because that governing equation carries a photon mass energy term, the experimental validation of massive photons is implicit in the results, in those two a priori results. Okay, so that's a first piece of really, really key evidence. So anyway, I plugged in different galaxies to see what answers I got, and this is all in those other papers that I mentioned. Now, the first sample size I tried was 10 galaxies, and I got pretty incredible results just from 10 galaxies, right? So from 10 galaxies, and they weren't cherry picked or anything. It was just what I could Google, right? 10 random galaxies that I just Googled. Anyway, what I actually needed was the size of the galaxy and the mass of the galaxy. So just from the size and from its mass, you can predict what the Hubble constant based upon that galaxy is. Now, when I just randomly selected 10 galaxies, when I averaged the result, it was remarkable. I actually ended up with a value basically equaling the CMBR Hubble constant. So remember, there are two Hubble constants here. You've got what I call the cosmological Hubble constant. That's what's measured, that's the background radiation, right? That we measure, those stretched microwaves. So that's the first type of Hubble constant, and the second is what I call the astronomical Hubble constant, and that is determined by basically studying bright lights, to put it very simply. Okay, so and those two Hubble constants differ by about 6 kilometers per second per megaparsec, and that difference of 6 kilometers per second per megaparsec, it sounds like nothing, and it was thought originally to be nothing. It was believed that when that discrepancy first appeared, that 6 kilometers per second per megaparsec would just disappear with improved resolution of measurements and data and all kinds of things. Well, no, the actual opposite has occurred. So what's happened is the cosmic distance ladder measurements, the astronomical Hubble constant, the way it's determined, has become increasingly accurate. So the error bars have narrowed, increasingly over time. So it became very obvious that these two Hubble constants could not be reconciled. So anyway, so that's the basis, that's the background of the problem and the basis of it. And as I mentioned just a moment ago, I plugged a few numbers in. Anyway, what I found was, in the 10 galaxies that I just randomly selected, I found that the average of that sample ended up being almost identical to what the cosmological Hubble constant is. So that implied that the Hubble tension It doesn't really exist. It's just fictitious. It's imaginary. Everything's fine. Everything's doing what it's supposed to be doing. We're just measuring our stuff incorrectly, right? Or not incorrectly, but we're biasing our measurements. This is what it means. So it's not. I used the wrong term a moment ago. There's nothing incorrect about it. It's just a measurement bias. Anyway, now when I showed that paper to Mike Peroni, and Mike looked at it. So, yeah, it's interesting, and he came back with a very good point. He said, look, there's only 10 galaxies here. I mean, you could have cherry picked them. And when he said that, because it's all via email, when he said that, I thought, oh, you bastard. I thought, yeah, well, he's right. You know, he's right. You know, so I thought I've got to fix that. So a few years went by. I think about 4 years went by. I think this was back in 2022 or something like this. And 4 years ago, 4 years go past, and I finally got round to actually determining how I can get access to these databases, right? So I actually downloaded and learned how to actually access a couple of key databases. Now, one is called the MaNGA database. So it's the final release of a massive study that was done, three-dimensional study that was done on galaxies, just recently completed. And I can't remember what the acronym for MaNGA is, MaNGA. You can look it up or you can read about it in my paper, but I can't remember what the acronym actually represents. But anyway, it's a database of 10,200 extremely accurate measurements of galaxies. It was part of a survey, right? So basically, you've got some fiber bundles. I write about it in the article. You can read it, right? But anyway, basically, you've got some fiber bundles. They look at at a point in light, and they look at a galaxy, and they gather a whole lot of information about it. This 2D information, which is then turned into 3D using the redshift as the third dimension. Anyway, a lot of very accurate information was gathered in that survey, and there was 10,200. Now, 135 of those were repeat measurements, and there was some other measurements in there that were incomplete and stuff. So I filtered out everything that was incomplete, basically, right? So anything that had the word NaN in any field, or there were fields with negative 9999, I think. And anyway, I filtered all of those out. So I ended up with 10,096 galaxies from the MaNGA database. Anyway, I ran those 10,096 galaxies through my equation, and it was absolutely astonishing. What I ended up with is a Hubble tension of basically zero. The Hubble tension reduced to zero if you average over a large number or an infinite population of galaxies. So this is absolute 110% confirmation that the Hubble tension is fictitious, it does not exist, and that we have actually resolved the Hubble tension with equation 1. Now, is something else. Now, because I felt that 10,096 galaxies wasn't enough, I went to another database which had over 15,000 galaxies in it, not with the same precision that the MaNGA database had, but still very, very useful. Anyway, I took out what I believe to be incorrect measurements, incorrect data in that galaxy. Again, same kind of thing, NaN or minus 999, these kinds of things, right? Anyway, and I filtered out what was obviously wrong. Anyway, I can't remember what it was, but it was just obvious that a good chunk of that data wasn't actually clean at all. Anyway, so I started off with over 15,000 in that database, and I ended up with 11,060. So I remained about, I had about 70% of the original database. Okay, so I then ran that same database, I ran that database over my same equation 1 again to see what results I got. And again, I was shocked to see the same thing. I got the same result as the MaNGA database result, which was convergence to the CMBR. So the Hubble tension disappeared. Doesn't exist. It's imaginary. It's not a real phenomenon. So I was totally shocked when I saw these results, because here we've got one of the significant problems, one of the most significant problems in cosmology that has just evaporated. Right now, remember, I started, as I mentioned before, I started with 10 galaxies, and I got it to converge after only 10 galaxies. I then pumped through 10,000 galaxies, and the tension vanished completely. I then pumped through another 11,000 galaxies, and once again, the tension evaporated. Okay. Now, I must mention that there's probably significant overlap between the second database that I used, which is labeled 50 MGC. So it's basically a massive survey of 15,000 galaxies within a 50 megaparsec distance from Earth, right? So they're nearby galaxies. Okay, so there's probably a huge overlap, but in my paper I don't merge those two databases, right? I don't put them together. I assume that there's a big overlap from one to the other. In fact, I assume that 80% of the galaxies in the 50 MGC database already appear in the MaNGA database. I don't know if they do, I just made that assumption. Right, so that means that only 1 in 5 of my original 50 MGC database samples remain. And when you add that to the existing MaNGA database, when you merge those two and you take your means and your standard deviations, etc., the Z-score you get from either one of these databases, or two even partially merged, is just absolutely enormous. And I write about this in the article. Basically, the probability of not having resolved the Hubble tension statistically is 0. Seriously, you can't even put it. You can't put it into a spreadsheet or any other machine at double precision and get anything other than 0. Right. So the results really are absolutely overwhelming and literally are irrefutable. I've never made this claim before, and I wouldn't be making it now unless I was absolutely certain. The results are conclusive, definitive, and irrefutable. All right? I don't mean to really push that barrow, but I'm just trying to emphasize just how certain, not myself, not how certain I am, how certain the mathematics are. And here's something very, very important that I want to point out to you guys as well. Now, I had to determine from each one of those two databases what the actual radius is of a galaxy in terms of kiloparsecs. So So the way the data is gathered and stored, it's stored in angular terms. Okay, so I had to convert that angular measurement into what I needed. So how did I do that? Good question, I'm glad you asked. Well, the way that I did that was I just used a standard off-the-shelf equation. So an off-the-shelf, astrophysics equation, and you can find that in the paper as well. But the important point I'm getting to, is that basically to use that equation, that off-the-shelf standard cosmology equation, it requires the Hubble constant. So what I did was, because I wanted to stress test my solution and ensure that I have absolutely no bias, I plug into that standard astronomy equation. I plug into that the cosmic distance ladder Hubble constant of 73 kilometers per second per megaparsec. That then goes into equation 1. Okay, so just think of it like this. 73 goes into equation 1, 67 comes out. All right, so there's no circular logic, there's no tautology, nothing like that. All right, nothing like that, because of course, as you can imagine, I've run the paper through AI, countless times, and every time that you put it through, it says, oh no, it's circular logic, until you explain it to AI, and it says, oh well, wasn't I silly, But anyway, so I just wanted to mention that up front. So you put 73 in, you get 67 out. All right, so equation 1 really does do what's written on the tin. All right, it really does do what it was intended to do. I was surprised. I was shocked to see that it worked on any galaxy, right? And something else I want to point out now, at the front of equation 1, there's an experimental relationship function that I call K sub G. Okay, now that experimental relationship function is an artifact of the BPT method, right? So you have to put that in to the equation, because that experimental relationship function tells you how similar your solution is to reality. If it's perfectly similar, K equals 1, or in this case, KGE equals 1, right? If it's perfectly similar. So if what you've come up with in your head matches physical reality, that will equal 1. If what you've come up doesn't, you'll end up with something enormous or something very, very small. Okay. What I did was I set for all of those over 21,000 calculations, I set K sub G equals 1 for all of them. Okay? There's no fine-tuning, no dodgy stuff going on at all, right? It's K sub G equals 1 for all of them. Okay? So I just want to point that out, because again, you put that through AI, and AI, acting like a gatekeeper, blah, blah, blah. So I just wanted to mention that to you, right? Because if you do download it and you put it through AI, you'll get the same kind of rubbish that I got. So everything's above board, everything's honky dory. So yeah, I just wanted to sort of mention this in this video. I wanted to talk to you guys about it. Immediately following after this, after my little chat with you here, you're going to see, and please stick around for it, I used AI to generate one of those explainers, right? So look, viewers, I realise, people don't like to, watch or listen to AI and stuff. Look, I get all that, that's why you've got all these new kinds of AI things coming out to, showing all these flashing, twinkly things to keep people's attention. I get all that, right? But look, seriously, viewers, if you can just stick around, listen through to the end of it, and you'll really have a solid understanding of what it is that we have achieved in this latest bit of research. It is really groundbreaking. There's no other way to put it, and we have absolutely proven beyond any doubt that photons are massive. And by the way, just on that topic, all of this business you might hear about gauge invariance and you know what, viewers, you can chuck all that out the window. Why? Because if photons have innate mass, the entire gauge invariance problem does not apply because symmetry breaking never occurs. The standard model of particle physics always assumes that photons start off with zero mass and then maybe somehow acquire mass. And you need a mechanism to explain that symmetry breaking. However, if photons if they possess innate mass, that entire symmetry breaking problem does not occur. It doesn't need to be there. It's rubbish, right? So this is why I say to you that we have irrefutably, infinity%, absolutely resolved the Hubble tension, and in doing so, we have also literally proven that photons are massive. All right, viewers, I'm going to let you go. Look, thanks for your time, and look, please stick around and listen to the to the voices after this. They do a great job in explaining this latest paper, this latest article that we've written. So I'd really appreciate it if you could do it. I realise it's boring, etc. Blah, 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 do it for me, right? Do it for Ricky, all right? All right, viewers. I'll talk to you soon. Cheers. Bye.
All right, let's jump right into this explainer and crack open what is arguably the biggest paradox in modern cosmology. For years, astrophysicists have literally been tearing their hair out over a massive contradiction regarding how fast our universe is actually expanding. It's a mystery so deep that it's driven some folks to question whether our entire standard model is broken, or if we need to invent entirely new exotic physics just to make the math work. But what if the answer isn't new physics at all? What if it's simply a matter of where we're standing when we take our measurements? To really grasp the problem, we have to look at the discrepancy itself. Astrophysics has been facing this huge roadblock because our two gold standard measurements for the universe's expansion rate completely stubbornly disagree. On one hand, we have measurements from the early universe, derived from the cosmic microwave background radiation, basically the afterglow of the Big Bang. That gives us a Hubble constant of roughly 67.4 kilometers per second per megaparsec. But then, when we measure the late universe locally using the cosmic distance ladder, which relies on observing bright stars and supernovae, we get a value of 73. Now, these two numbers should absolutely match, but they don't. That gap is what scientists call the Hubble tension. So, to figure out why the laws of physics seem to be misbehaving, we've kind of got to treat this like a cosmic crime scene and dive into the newest evidence. We have to ask ourselves, are the measurements just wrong? Or is our underlying assumption that the universe expands exactly the same way in every single location fundamentally flawed? Well, some incredible recent research presents a definitive resolution, and it uses a truly staggering dataset. 10,096 independent galaxies from the final SDS-DR17 MaNGA data release. We aren't just looking at a handful of localized anomalies here. We're talking a vast statistical scale. This dataset represents the largest integral field spectroscopy survey ever conducted. That means we capture the entire visual footprint of a galaxy all at once, giving us over 10,000 distinct cosmic laboratories to test how space-time actually behaves. The research calls this approach tree ring dating for the cosmos, and honestly, that hits the nail on the head. Because instead of just seeing a galaxy as a generic, fuzzy blob of light, this massive dataset gives us a comprehensive, spatially resolved map. We get to see stellar kinematics, exactly what the stars are made of and precisely how they're moving. It essentially allows us to dissect a galaxy's entire life history. To really appreciate how revolutionary this is, think about the technological leap here. Historically, traditional galaxy surveys used a single fiber optic cable. They'd capture this one single blurred measurement of a galaxy's center. It was kind of like trying to understand the layout of a whole city by peeking through a single keyhole. But the new method uses custom-designed fiber bundles to create full 3D data cubes. Instead of treating a galaxy as a single dot, we now have 3D maps capturing thousands of distinct data points across the entire structure of the galaxy. And here is where it gets absolutely fascinating. This 3D mapping reveals the exact mechanism causing our measurement issues. Local space-time behaves like a drain. According to the research, galactic structures act as space-time drains. Within a galaxy, space-time isn't just undergoing that general outward cosmological expansion that pushes the whole universe apart, it is also simultaneously flowing inward toward the galaxy's center of mass. This dual influence creates a highly localized stretching effect. So, if you compare the dense centers of galaxies to their chaotic outer edges, you see a stark discrepancy in how space-time behaves locally. The centers of galaxies, what physicists call virialized cores, are gravitationally settled. They're dynamically stable. They are tightly bound to the cosmic frame, which makes them incredibly accurate representations of the true global expansion rate. But the peripheries, those outer edges, are chaotic, unrelaxed, and dominated by inward falling material. Any measurements taken out there are systematically inflated because of that local space-time stretch. Which brings us to the crucial point. Our previous measurements were accidentally biased. Why? Because we were exclusively looking at the bright, stretching outskirts of galaxies, completely missing their stable centers. For decades, astronomers relied on standard candles, like Cepheid variables and Type A supernovae. They're brilliant and easy to spot at vast distances. But those objects live almost exclusively in the chaotic peripheries of galaxies. We systematically avoided the crowded, dusty galactic centers because they were just too hard to measure. Until now, we basically created a cosmic optical illusion by only looking at the most dynamically biased locations in the universe. But this research introduces a single, perimeter-free, unifying mathematical framework that proves this isn't just a coincidence, it's a systematic correction. The research states it perfectly. 73 goes in, 67 comes out. There are no free parameters here, zero tuning, no fine adjustments. It is a fundamental equation that bridges the gap between local dynamics and global expansion. Let's look at the ultimate stress test for this and see how it builds a mathematical proof without needing to invent any new physics. First, the study takes that inflated local distance ladder value of 73. Then they explicitly feed it into their framework across that entire unprecedented dataset of 10,096 galaxies. Finally, by actively correcting for the physical masses and radii of those galaxies, the output completely overrides the local bias and converges precisely to the true global rate. When they account for the local inward flow of spacetime in the galactic cores, the unified equation outputs a global mean of 66.95 kilometers per second per megaparsec. By averaging out the internal kinematics over 10,000 galaxies, rather than just zooming in on their bright, messy outer edges, that inflated value of 73 just drops away. The true, stable cosmological expansion rate finally reveals itself from the data. Think about that number for a second. That derived output of 66.95 is statistically identical to the early universe CMBR value of 67.4 to within less than 1%. That massive, highly debated gap between the distance ladder at 73 and the cosmic microwave background completely vanishes when we apply the MaNGA dataset output. It proves that both measurements are actually correct within their own context. They've just been measuring entirely different physical space-time environments this whole time. Now, you might be thinking, okay, but could this just be a random statistical fluke? The data says, absolutely no way. With a vast sample size of over 10,000 galaxies, the statistical evidence here is completely overwhelming. The analysis yields a staggering z-score of over 422. To put that into perspective, a z-score of just 5 is usually the gold standard for a discovery in physics. At 422, the probability of this being a failure is mathematically indistinguishable from zero. It boasts a literal 100% probability of successfully resolving the tension. So what's the big takeaway from all this? It's that our standard model of cosmology is perfectly fine. It just requires applying the correct spatial math that accounts for local gravity. General relativity remains completely intact. We don't need to invent exotic, wild concepts like early dark energy to fix our math. Instead, we just need to use the mathematical tools developed way back by Georges Lemaitre for an inhomogeneous universe. We have to stop pretending the universe is perfectly uniform on a local scale and embrace that space-time is dynamic, rich, and heavily location-dependent. We've essentially discovered that our biggest cosmological paradox wasn't a crisis at all. It was just a mathematical illusion caused by where we were standing. The universe wasn't failing us. We were just failing to account for the gravitational weather right in our own cosmic neighborhood. By looking exclusively at the turbulent edges of galaxies, we skewed our entire perspective. But once we step back and look at the whole stabilized picture, everything aligns perfectly. It really makes you wonder, doesn't it? If local space-time stretches our reality this much, what other cosmic mysteries are just waiting for a simple change in perspective? We've solved the Hubble tension not by breaking the laws of physics, but by finally observing the universe with the nuance it actually deserves. So as we continue to gaze out into the cosmos, we really have to ask, what other assumptions are we making simply because of the highly biased gravity-warped location from which we are looking? Definitely something to think about the next time you look up at the night sky.